Hello! In this video, we are going to prove the following theorem. Suppose f is a function from the closed interval a comma b to r, and f is continuous on a comma b. Then f is bounded on a comma b. Now, in proving this theorem, we are going to be using the concept of partitions of an interval. So if we consider our closed interval a comma b, well then, a partition of a comma b is a collection of non-overlapping closed intervals whose union is a comma b. So for example, something like this would be a partition of a comma b. And we might label these closed intervals I1, I2, and so on. And we might label the endpoints of these closed intervals as x0, x1, x2, and so on. Now, a tagged partition is when we select a point from each subinterval of the partition. So, for example, let's say we select these points. Each of these points that we selected are called tags, and we might label the tags T1, T2, and so on. So this collection of subintervals, along with the tags, is what we call a tagged partition. And the way we label a tagged partition is usually a letter with a dot on the top. And the collection is pretty much the collection of subintervals along with the tag in each subinterval. So just like that. Now let's talk about what a gauge is. A gauge on a closed interval a comma b is a strictly positive function defined on a comma b. For example, the function given by delta of t equals t squared plus 1 for each element t in a comma b would be an example of a gauge on a comma b. Right, so that's what a gauge is. Now, given that delta is a gauge function on a comma b, and given P is a tagged partition of a comma b, we say that P is delta fine if the following is true. We say P is delta fine if each subinterval of the partition is a subset of this interval. And this is an interval centered at the tag of the subinterval. And the way you can visualize this is if we consider our subinterval II, which we'll say is right here, and we'll say that the tag Ti is located right here. Well then, this interval is an interval centered at the tag, and its radius is precisely delta of Ti, right? The radius is the output value of when you send Ti into the gauge function. So this interval, centered at Ti, might look something like this. So for a partition to be delta fine, we need each subinterval to be a subset of this interval, which is centered at the tag Ti. So for example, for this partition to be delta fine, we would need I1 to be a subset of this interval centered at T1. We would need I2 to be a subset of this interval centered at T2. We would need I3 to be a subset of this interval centered at T3, and so on for each subinterval. Now, a fact which we have proven is that if delta is any gauge function on a comma b, then there does in fact exist a delta fine partition of a comma b. And so, this is really the concepts that we're going to be using to prove this theorem. Okay, so now let's get into proving this theorem. To start out the proof, since f is continuous on a comma b, this means that f is continuous at every point in a comma b. So if t is any point in a comma b, well then to say f is continuous at t means the following. It means for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in a comma b, if absolute value of x minus t is less than or equal to delta, then absolute value of f of x minus f of t is less than or equal to epsilon. Now, this definition is equivalent to if these are instead strict inequalities, right? But we're perfectly fine if we have weak inequalities here, because it's equivalent. So then, if we consider an arbitrary element t in a comma b, well then, f is continuous at t, which means this statement is true. And this statement works for every positive real number, so in particular, it must work for the positive real number 1. So taking epsilon to be 1, we have that this statement is true. So there exists a delta greater than 0, such that for all x in a comma b, if absolute value of x minus t is less than or equal to delta, then absolute value of f of x minus f of t is less than or equal to 1. So what this tells us is, given any element in a comma b, we can map it to a positive real number which has this property. Give me another element of a comma b, we can map it to a positive real number with this property. You give me another element of a comma b, we can map it to a positive real number with this property. So this is essentially giving us a function, mapping each element t in a comma b to a positive real number delta of t with this property. And delta is a strictly positive function defined on a comma b. So delta is a gauge on a comma b. And since delta is a gauge on a comma b, well, we know that there exists a delta-fine partition of a comma b. I'm going to call that partition P. And we'll say that the subintervals of the partition are symbolized by II, with a tag symbolized by Ti, from I equals 1 to n. Now to show f is bounded on a comma b, the idea is we consider the maximum value of the list absolute value of f of t1, absolute value of f of t2, absolute value of f of t3, and so on up to absolute value of f of tn. We're going to call that value k. The claim is that we can show that f is bounded on a comma b by the value 1 plus k. In other words, the claim is we can show for all x in a comma b, the absolute value of f of x is less than or equal to 1 plus k. If we can show this, this tells us that f is bounded on a comma b by the value 1 plus k. So to prove this, let's give ourselves an arbitrary element x in a comma b. From here, we want to show absolute value of f of x is less than or equal to 1 plus k. Now, since the partition breaks up the interval into a bunch of subintervals, we know that x belongs to at least one of these subintervals. For example, x belongs to some subinterval II. But since the partition is delta fine, II must be a subset of this interval centered at the tag Ti. And therefore, x must be between these two values. And from properties of absolute value, this is the same thing as saying absolute value of x minus ti is less than or equal to delta of ti. So from here, we should be able to find a tag ti such that absolute value of x minus ti is less than or equal to delta of ti. But then, let's go to the definition of our gauge function. For each element t in a comma b, delta of t is a positive number with this property. So replacing t with ti Well then, delta of ti is the positive number with this property. So this statement is true for every element of a comma b. So in particular, it must be true for the element x we have here. But since we know absolute value of x minus ti is less than or equal to delta of ti, that's what we have here, we can conclude that absolute value of f of x minus f of ti is less than or equal to 1. But the claim is, from this inequality, it follows that absolute value of f of x is less than or equal to 1 plus absolute value of f of ti. And to see how that happens, well, let's rewrite this inequality right here. Well then, by the reverse triangle inequality, the absolute value of f of x minus f of ti is greater than or equal to the absolute value of f of x minus absolute value of f of ti. But every real number is less than or equal to its absolute value. So in particular, the absolute value of f of x minus the absolute value of f of ti must be less than or equal to its absolute value. So this shows absolute value of f of x minus absolute value of f of ti is less than or equal to 1. So adding absolute value of f of ti to the other side, we have that absolute value of f of x is less than or equal to 1 plus absolute value of f of ti. And that's what we get. But k is the maximum value of absolute value of f of t1, absolute value of f of t2, absolute value of f of t3, and so on. So absolute value of f of ti must be less than or equal to k. So this must be less than or equal to 1 plus k. And so this shows if x is any element of a comma b, then it follows that absolute value of f of x is less than or equal to 1 plus k. And that is exactly what we wanted to prove. So this shows that f is bounded on a comma b by the value 1 plus k. And so this completes the proof. And so yeah, that's pretty much it for this video.